Welcome, and get ready to dive deep into a topic that's quite literally shaping our future: wireless communication in 2030 and beyond.
That's truly fascinating. So if these are the incredible, almost dizzying goals we're aiming for, how exactly are we going to achieve them? Let's delve into the core enabling technologies that will make 6G a reality. We're talking about things like terahertz communication, reconfigurable intelligent surfaces, AI-native networking, non-terrestrial networks, and deep edge cloud integration. This is truly where the technical magic happens, where the theoretical becomes the practical.
This is indeed where the rubber meets the road, outlining the comprehensive and often groundbreaking technological toolkit that will underpin 6G, enabling those extreme performance targets.
Okay, let's start with terahertz. What exactly is that?
First, terahertz communication explanation. Terahertz communication utilizes extremely high frequencies, specifically in the range between zero point 0.1 terahertz, that's 100 gigahertz, and 10 terahertz. This range offers ultra-wide bandwidths, which are absolutely crucial for enabling the astonishing Tbps-level data rates that 6G targets. To truly understand terahertz communication, consider the shift from gigahertz frequencies, which 5G primarily uses, to terahertz frequencies as a transition similar to moving from traditional copper wires to high-capacity fiber optics. It's about unlocking vastly more capacity by using a much higher frequency spectrum, allowing us to encode much more data simultaneously.
Like fiber optics, but through the air. Sounds amazing, but what are the catches?
There are significant challenges. Because these waves are so incredibly small and high frequency, they act almost like tiny, delicate laser beams. They suffer from severe propagation loss over distance, meaning their signal strength diminishes very rapidly. They are also highly susceptible to atmospheric attenuation, particularly from water vapor and oxygen molecules in the air. Imagine trying to shine a laser through dense fog. The signal quickly dissipates.
So they don't travel far easily.
Exactly. This means their effective communication range on the ground is severely limited to very short distances, primarily for line-of-sight LOS applications. Conversely, in the vacuum of space, they can enable very long distances between satellites where there's no atmospheric interference. Furthermore, current hardware struggles to produce high-power terahertz transmitters and sensitive, low-noise terahertz receivers. These are essential for stable and reliable signal generation and reception at these ultra-high frequencies.
Okay, big challenges. How do we solve them?
Several innovative solutions are being developed. Ultra-directional antennas and high-gain beamforming are crucial to precisely direct and steer terahertz beams, acting like powerful spotlights to concentrate the signal and compensate for rapid path loss. Multi-hop relaying can extend the communication range by retransmitting signals over shorter segments. Tunable intelligent surfaces, which we'll discuss next, are also vital for intelligently reconfiguring the wireless environment to guide signals around obstacles. And photonic integration, using light-based technologies to reduce coupling losses and enable multi-antenna systems on a chip, is a promising solution for improving both transmitter power and overall system efficiency, making terahertz devices more practical and scalable.
Okay, so highly focused beams and smart surfaces. Let's talk about those surfaces. Reconfigurable intelligent surfaces, or RIS.
Next, we have reconfigurable intelligent surfaces, RIS. Explanation. RIS are truly innovative and somewhat counterintuitive components. They are essentially small, passive, and modular devices. Think of them like smart, programmable mirrors for radio waves that can dynamically reconfigure the wireless propagation environment. They achieve this by intelligently altering the phase shifts of the radio signals they receive and reflect. This unique capability enables precise, intelligent steering of wireless links, effectively create smart walls or smart windows that can improve network robustness, extend coverage into dead zones, and enhance overall reconfigurability.
Smart mirrors for radio waves. Interesting. What are the benefits?
The advantages of RIS are compelling and align strongly with 6G's goals. They are easy to deploy in various environments due to their small form factor and modularity. They offer highly sustainable operation due to their negligible power consumption, making them a key building block for green communication systems.
Low power consumption is huge.
Absolutely. By actively shaping the radio environment, RIS increases overall system efficiency and dramatically improves spectrum utilization. Unlike 5G, where beamforming is primarily active and controlled by energy-intensive base stations, 6G will leverage RIS to shift beamforming towards a more distributed, passive-active model with AI-based adaptation, offloading some of the energy-hungry tasks.
Sounds great. Any challenges with RIS?
Developing RIS components that can efficiently operate at the incredibly high Thertz frequencies poses specific challenges. It requires novel tuning mechanisms and advanced materials, including cutting-edge CMOS transistors, high-speed Schottky diodes, innovative graphene-based elements, and precision MEMS for dynamic control. Still work to be done there.
Okay. Now let's revisit AI native networking. You said it's core to 6G.
Yes, a core and transformative vision for 6G is AI native networking. Explanation. This concept goes far beyond simply using AI as an overlay tool. It involves embedding AI at every single layer of the network stack, from the physical air interface right up to the application services. The goal is to create a truly self-optimizing, self-healing network that can anticipate and respond to user needs and dynamic network conditions in real time, operating with minimal human intervention.
How does it function differently?
Functionality. AI-native networks facilitate pervasive AI-centric operations across the control plane, user plane, and even higher-level application elements. Large language models, LLMs, and generalized pre-trained transformers, GPTs, will be central to this intelligence. They will handle complex tasks like understanding nuanced user intent, strategizing optimal network configurations, and executing intricate commands for highly autonomous network management. This includes sophisticated traffic prediction, real-time anomaly detection, and even generating hardware description language, HDL, code for wireless systems to boost design productivity. The AI interconnect framework detailed in the Alpert report will provide crucial messaging and brokering capabilities for these LLMs across different network planes, allowing them to collaborate and share insights.
Give us some practical examples.
Examples. Practically, AI will enable real-time network automation, dynamic and predictive traffic management, seamless handover optimization between cells without drops, and the creation of self-healing networks that automatically detect and repair errors, often before users even perceive an issue. This also extends to optimizing power consumption across network layers for enhanced sustainability.
Okay, AI is truly embedded. What about connecting the unconnected NTNs?
Fourth, we have non-terrestrial networks, NTNs. Explanation. NTNs, which crucially include constellations of low Earth orbit, LEO, and geosynchronous Earth orbit, GEO satellites, are absolutely critical for complementing terrestrial networks and providing pervasive, truly global coverage. This extends connectivity to previously unconnected regions like polar areas, remote oceans, vast land masses where terrestrial infrastructure is impractical. They enable ubiquitous connectivity by seamlessly integrating terrestrial, aerial drones, high-altitude platforms, maritime, and satellite networks into a single, cohesive, multi-dimensional system.
How do these satellite networks work?
Architecture. NTNs can employ different payload types. Transparent payloads act essentially as analog repeaters, simply amplifying and relaying signals between the ground gateway and the user equipment, like a mirror in the sky. More advanced regenerative payloads actually have full GNODEs on board the satellite. These GMBs can process signals, perform routing, and crucially enable inter-satellite links. These are mandatory for achieving truly global coverage and efficient routing across vast satellite constellations without constantly bouncing signals to ground stations.
Sounds complex. What are the big hurdles?
Challenges. NTNs introduce unique and complex challenges. High latency is a significant concern, especially for GEO satellites due to long propagation delays. LEO satellites, while closer, introduce significant and rapidly changing Doppler shifts due to their extremely high relative speeds, around 7.56 kilometers for a 600-kilometer LEO.
Doppler shifts, like ambulance sirens changing pitch.
Exactly, but for radio waves. This rapid movement also leads to complex mobility management issues, like frequent and challenging handovers between rapidly moving satellite beams as a device travels.
So how do we handle that?
Solutions. Innovations are vital. These include advanced timing, advanced TA refinement to compensate for signal travel time, enhanced two-step random access channel RACH procedures to mitigate long delays during initial connection setup, and sophisticated handover mechanisms like those triggered by precise location-based information, leveraging the deterministic movement of satellites and accurate ephemeris data. Pre-provisioning satellite orbital parameters to user equipment is also key.
Okay, lots of smart engineering needed. Lastly, edge cloud integration.
Lastly, edge cloud integration is critical to realize the distributed intelligence of 6G. explanation. 6G will rely on a flexible and dynamic computing continuum, seamlessly integrating computational capabilities from local edge computing clusters located very close to the user to centralized cloud resources. Edge computing clusters will handle real-time, latency-sensitive AI workloads like complex AR/VR frame synthesis needing immediate processing or critical industrial automation tasks where instantaneous decision-making is paramount. This decentralizes data processing, minimizing round-trip time and improving responsiveness. Cloud resources, on the other hand, will manage larger-scale data processing, extensive AI model training, and less latency-sensitive tasks.
What's the synergy between edge and cloud?
Synergy. This deep integration supports highly user-centric approaches, allowing for dynamic scripting of new AI model training via edge-federated learning. In this paradigm, models are trained locally on devices at the edge, and only aggregated insights or model updates are shared with the cloud, preserving privacy and significantly reducing backhaul traffic. This creates a powerful distributed learning system.
Sounds efficient. Any challenges there?
Challenges. Implementing this seamless continuum brings its own set of challenges. Managing the immense communication demands between edge and cloud nodes, addressing the significant computational intensity required at the edge for complex AI tasks with limited resources, and solving complex data storage concerns in decentralized edge environments while ensuring data consistency and security.
That's a lot to take in. It's clear that the future of wireless is a symphony of complex, interconnected technologies working together seamlessly, each solving specific monumental challenges to achieve this hyper-connected, intelligent vision. It's an incredibly intricate puzzle.
We invite you to explore the full analysis. A comprehensive and detailed review of the Alpert Research Team's presentation on the future of wireless communication is available at the following link.